analysis of master theorem. Let's suppose we have a recursive algorithm. So now what we will do is we will actually convert this recursive algorithm in a recursive tree. So I'm going to take an example of a general recursive algorithm. So let's suppose the algorithm converts a whole problem in two subproblems, or let's suppose it converts into three subproblems. So let's suppose initially the problem is having value a, and then it divides it into three parts. So you can see that it will go on dividing this subproblem into three parts, and again it will divide it into three more parts. So any recursive algorithm will kept on dividing the subproblem into a parts, or I should say in three parts. So what we are going to see here is that the depth of this whole binary, it's not a binary tree, so I should say that it is a tree, and tree has a depth of log base bn. So we know that after every step it is actually dividing the whole problem into some certain types of subproblems, and let's say that it divides it into b subproblems. So this will give me the depth as log bn, because you can see that, let's suppose we have a binary tree. Let's take an example of a binary tree. So this problem, this is the main problem. I will write here that this is the main problem, and it divides this whole problem into two subproblems, and then this problem is again divided into two subproblems, and this will go on and on like this. So you can see that this is actually a binary tree. This is basically a general case, and this will be a case of a binary tree. So you can see that if there are n inputs initially, now inputs will become n by 2 at this step. In the next step, it will become n by 4. So it is actually dividing the whole problem into two parts after each step. So this basically gives me a depth of log base 2n. Remember, b represents the number of inputs each subproblem is taking, which is the half. So we're considering b as 2, because you can see that it will just divide it into two half arrays. So that's the main reason why we are taking the depth of this tree or any general tree as log base bn. And we know that the number of children which is a. In this case it is 3. If it will have more children, we are going to represent it with a. So now you can see that if we divide any recursive algorithm into subproblems, we can get a depth of log base bn, which is 2n in this particular case. So if I say that depth of I contains a raised to the power I nodes. So let's suppose at some depth I, so I can represent any natural number. So I can calculate the number of nodes at any depth. So let's suppose I want to calculate the number of nodes at depth 2. I can basically write it as, this is depth 1, so I will write it as 3 raised to the power 1, which will give me 3. If I will consider depth 2, it will give me 3 raised to the power 2. So you can see that A represents the number of children, and if I consider any depth, if I want to consider a particular depth, we know that it will give me A raised to the power I nodes are there in that particular depth. So at depth 2, we will obtain 9 children. So this is the basic reason behind this. So let me show you a basic. I'm going to perform some basic mathematics here, which will help us in getting n log b by a, log n raised to the power log base ba. So this is what we will have to get, right? So let's suppose I say that there is, if y is equals to b raised to the power x, and if I can write this as x is equals to log base b y. So I can write it like this, and further if I want to solve it, I can solve it. If this is what we have got, you can see that I can compare this value with log base bn. So here y is equals to n, so I will get the value x is equals to log base bn. So you can further evaluate this whole value as n is equals to b raised to the power x. So you will get this value at this point. So b is actually so x basically represents the depth of the tree. X represents the depth of tree. You can see that the value of x is equals to log base b y equals to n, so it will be log base bn, and we know that the depth of a tree is log base bn, so x equals to log base bn. So this is basically similar to this equation. So this basically represents n equals to b raised to the power x. So let's suppose b is 2 in our case, so it will represent 2 raised to the power x, where x is the depth of the tree. So if I will consider this equation, you can see that a raised to the power log base bn. So this basically represents this equation. As you can see that 2 is b, so you can see that 2 is b in this case, and n is y, and a is the number of children. So you can see that depth of I contains a raised to the power I nodes. So if I will consider that the depth is log base bn, that means it has these number of nodes, then the depth of I will contain a raised to the power log base bn nodes. So this can be re-evaluated as n raised to the power log base ba. So basically the depth of I contains a raised to the power I nodes represents this equation. So this means that if the value is n log b by a, it represents the depth of I nodes, and we know that I node or the depth I is basically log base bn. So I've just used this mathematical concept to represent and to compare it with this equation. So we now know how we have got this value. A raised to the power log base bn basically represents a raised to the power I nodes, and I know I is the depth, so simply I is log base bn. So this can also be written as n raised to the power log base ba. So at any particular depth, I have a raised to the power I nodes or these number of nodes. So this will be the runtime of the whole recursive algorithm. And now that's the main reason why we are comparing this value with a particular function which is asymptotically positive. because if I will compare this function with this value, I'm actually comparing this function with the runtime of these number of nodes at any particular depth, which is log base bn. So this is the basic analysis of the master theorem, where I've explained the depth of a tree, and I've explained how we have got this value n raised to the power log base ba, and why are we comparing this value with the function. So that was our main motive. You can see that in the whole master theorem, what we were actually doing is we were actually comparing this value with the function. So we have obtained this value, and we know that what this value represents. We know that n raised to the power log base a represents the depth of I nodes, and I basically represents log base bn nodes. So the runtime of these number of nodes, we will compare it with some function which is asymptotically positive, which means it has a higher value, and by comparing it we will get the these three cases. And in this manner we have analyzed the master theorem, and we have used the master theorem in the merge sort algorithm, so you can now apply it in any further recursive algorithm. So we will just analyze these cases. So thanks for watching.